So it is my great pleasure to introduce to you Dr. Bram Stieltjes. Bram is Vice Chair of Research of the Department of Radiology and heads the Department of Research and Analytical Services in IT at the University Hospital in Basel. He is trained in radiology, radiation therapy, and child psychiatry, and holds a PhD in the field of image analysis. And Bram has a broad experience when it comes to interdisciplinary work between physics on the one side, computer science, and medicine. In 2014, Bram moved to Basel, where he currently works on hospital-wide data integration and extraction in a clinical context for both research and diagnostic purposes. Bram will present to us today his SPHN infrastructure development project entitled Quality Assessment for Interoperable Quantitative CT Imaging. This project was jointly funded by SPHN and PHRT in 2018, and we are very curious to hear about the progress of the project. Welcome, Bram. Thank you for being with us today. We are looking forward to your presentation.
Yeah, thanks, Catherine, for the introduction. I'm going to try to put the project in a bit of a broader sense. I hope that makes it a little bit more interesting, because CT is only one of the, let's say, imaging methods that is important also for SPHN. Yeah, let me get started with that. Let's see, yeah. So I will try to give kind of a broad view and a narrow view. Then specifically, I will just, so that those of you who have nothing to do with CT and radiomics, I will try to explain a little bit what it is and why it is important to this project. Then I will quickly say where we are with this project. And then in the end, I will at least try to expand a little bit what we try to do in this project to what I think is necessary in general in SPHN, and why this project is maybe also kind of a model for what you need to think of. So generally, we are confronted with a huge amount of data that is increasing, data doubling times are now approximately thought of to be like 2 years. So basically, in every 2 years, clinics are hit with double the amount of raw data, let's say it like this, that needs to be kind of worked on in some way to make it medically interpretable. And then we have like all kind of fancy sounding things like multi-omics, radiomics, virtual reality, and then the whole thing about AI with convoluted neural networks, machine learning. It sounds all very spectacular. And then on the, let's say, clinical side, we have budget cuts, MD shortage, this data avalanche I just alluded to, and value-based medicine, all kinds of things that, well, are somehow related, but in reality difficult to relate. And sometimes, well, I'm more or less in the middle, and I am not as flexible as this Jean-Claude Van Damme. So it's really challenging. We are in desperate need, I think, for automation of processes and different ways of extracting parameters, both for clinical use, but even more so for research use. So, is there no automation of quantification in medicine? Actually, there is, and this is an example I like to give. Of course, you know I'm Dutch, and I have to stress that microscopy was invented by a Dutch guy, and they were looking at you see this very old drawings of the publication of Royal Society of red blood cells, and then it took us quite a while for Coulter to kind of I think in the 60s of the past century to kind of automate this this process, and basically now to measure a hemoglobin, nobody is looking into a microscope anymore. But there is a machine that basically indirectly quantifies the amount of hemoglobin in without anybody touching it. And I think that looking at laboratory medicine as an example of how imaging got automized is actually quite helpful in a sense, because it shows you some components that are important, and that's the calibration, the automation, and then in the end, the quantification. And if you look at a lot of scientific projects, they basically start with the quantification. So they take images, CT, MRI, microscopy, histopathology, it doesn't matter, and start quantifying. But they don't think at all about calibration and automation. And thus, it's neither reproducible nor scalable. So that's really a big problem. And I will try to allude to you why calibration, I think that will be my main topic, like calibration of CT. So that's the quality part, is so important, and how it's like a prerequisite. And then still you have to think about automation, and then you can do quantification. Also in large-scale research projects like SPHN. So for those of you who are not radiologists, I just wanted to kind of quickly show you, like you see here on this image, really a typical radiologist looking at CT images, and basically what he does is looking at them and then transforming all these gigabytes of data into a kilobyte unstructured text file. So it's a huge data reduction. We hardly do any measuring in a clinical radiological report because it is very time consuming. Imagine I have a patient with 10 tumors and I have to draw lines all the time. It's not feasible within the time that we have in clinical context to achieve. So if you were to read a radiological report today, you would be surprised how little numbers there are in such a report. And I think that's important to stress, because I think a lot of people outside clinics believe we would do much more quantitation in a clinical routine than we do. And the reason why we don't is that it is not automated and thus very time consuming. So that's important to know. And basically, people then just talk to a microphone like this guy here, and what you get is a doctor's letter. And what it creates, both for clinical but also for research purposes, is like a Babylonical speech chaos. There is no standardized report, there is no quantification. So now we want to do research on, let's say, using imaging as a biomarker for how a tumor is responding to a therapy, for instance, but it's all very non-quantitative. So there's a gap there, and from clinical routine you will not get the data that you will require for projects like this. So, of course, both from a clinical perspective, but even more so from a research perspective, we do think about this, like what can we do, and how. So can we make a future that looks very similar to what already happened in laboratory medicine, and hopefully not take 300 years to go from looking at it through a microscope personally to putting a sample into a machine. And so this would be a cycle that we're thinking of, and it really has these critical steps: calibration, automation, extraction of quantitative values. And then you can kind of create a quantitative data cycle that also improves the way you generate images, and of course gives you a rich data set for analysis. And whereas today the focus is very much on CT, we have another project that we are part of, the Imagine project, where we're basically doing something very, very similar for MRI. And what I would love to kind of get through today to you is that actually I can exchange now any machine, like could be an MRI, could be a CT, an ultrasound, it doesn't matter. This topic will come back to you all the time. If you don't address it, you don't have a real project, I think. But it's largely ignored. So to be able to kind of discuss with you a little bit what we're doing, I thought I'd just throw in some very, very basic CT. So I'm not going to explain how a CT works, but on the right-hand side, you see a CT image. This is a piece of the lung. This is the vertebra, so the ribs and the spinal column. And here you see a large heterogeneous lung tumor. This is a CT image. And the gray values that you see correlate to densities that have been defined by Sir Hounsfield. And so this is Hounsfield units are describing basically the density of the tissue, and they scale from 1,000 for bone, 0 for water as a calibrating a middle, and 1,000 for air. So basically here you see the lung almost has no signal, so that's -1,000, and bone here is very bright. So it's basically a density measurement, and it's quantitative like this. So it's not a relative quantitation that you would have in MRI, but really a more or less hard quantitation. So that's the basics you need to know. So there's Hounsfield units that are quantitative units that describe the density of the tissue that you measure with the CT experiment. And then you can calculate an image like this. Now, again, we normally in clinics would then describe this tumor. So it is very irregular, it is heterogeneous, and it has a certain diameter. I think at best we would draw a line here and say it's 5 to 10 centimeters, something like this. That is what you would find in the report. And it's very interesting because this heterogeneity, for instance, is an important information if you want to judge the tumor, because if you have highly aggressive tumors, they might have very vital parts where the tumor is growing very fast, but also liquid parts where there is necrosis. And typically the idea is that the more heterogeneous the signal is inside the tumor, the more likely this is that this is a highly malignant tumor, whereas the more benign ones will be more homogeneous. And this is basically where the whole field of radiomics come from. It's like, can I describe the content of this bag of pixels and draw some more advanced kind of information from what it is? But it's always a representation of something that kind of we already see. I see this is heterogeneous, but there's no number to it. So that is, in a nutshell, radiomics. First of all, I think radiomics got radiomics because this is a way to get funding, because we have genomics, proteomics, and then of course the field of imaging also needed omics. So we have radiomics. And basically there are a few steps, and this is from a very simple webinar on radiomics. It's like, okay, you need the image, and then it already gets exciting for me because you don't want to have a statistical value of all the voxels because most of it is air. You need to extract the tumor to do meaningful analysis. Now, in most publications, people do this by hand. That's a huge problem because depending on what I draw, I get different signal distributions. This is a topic I will not address today. This is more the step of automation. Like, how do I recognize a tumor? How do I segment it automatically? Because if I don't do that, it's impossible to do reproducible radiomics. Actually, in this project, we are in this part where the logic is, here we look at signal distribution, and this signal distribution is highly dependent on how the image is acquired and what is the quality of the image. So if we don't control this statistical distribution will look very different. And what the biomarkers, the quantitative biomarkers that we extract from this tumor, will look very different depending on the quality of that image. So, but where you have a problem in both steps. So if you don't control this statistical distribution will be very, very different, and your conclusions will be very, very different on what biomarker will be predictive and what it means. Next step, this segmentation is just as important. It's just not part of this project, but it would be equally important to have a stable method to extract this thing. Again, if you look at most radiomics presentations, this is something that is always ignored, and this is something that is mostly ignored. So that makes it kind of questionable what people draw for clinical conclusions out of statistical distributions acquired like this. So where are we in this project? So to be able to reasonably assess the quality of a CT dataset, for a long time already, people have developed so-called phantoms. So phantoms are measurable objects that we exactly know the geometry of, that we know what is in there, what is the density, and so on and so on. So they serve as a reference that we know, because we don't know exactly the real size of this tumor, the real shape of this tumor. And of course, such an object you can move then from scanner to scanner and from hospital to hospital and kind of get on the same object an answer back on what this machine will provide in terms of data quality. And there are simple phantoms like a sphere filled with water, and this you can use for rough, let's say, calibration of the machine, but it will not give you an information on how the quality of the data will affect the statistical analysis of the content of a tumor like this. So the phantom in itself must be, let's say, complex enough to really tell us something about the effect of the data quality on the post-processing pipeline after image acquisition. This has been really exciting. What can be done is, this is an original CT dataset, and what you can take that and print iodine on paper, and iodine has its own density, and depending on the concentration you can mimic the densities of an original CT dataset, but and then you can print a stack of papers. That is what you can see in the middle image, and then what you get out is actually this is the phantom data of the original dataset. So what you see here is not an actual patient, it's actually a stack of papers filled with different densities of iodine. So like this, we know more or less exactly the real density that we have here, and we know the exact shape. And this object can be moved from hospital to hospital. We can assess protocols, and we can do the whole post-processing analysis, and then see like, okay, if I use this scanner, that scanner on the exact same phantom, do I get exactly the same values or not? And how do the different qualities, artifacts that we get in different scanners affect the overall quantification pipeline? And we've been going through quite some optimization. So with the different papers, then with ways to cut out the lung tissue to have air there. And the other thing, we also looked at this kind of having test patterns, like these stars where we know the angle between the lines, and we know the resolution, the density between the rings, so that we have a phantom that copies both the, let's say, the clinical anatomical situation, but also a more formal measurement of image quality. And this is what came out, I think, roughly a month ago. So this black box you see here is a stack of paper encaged in this plastic. You can see a cross here that we can use to exactly align. There's a laser system on each CT scanner. I think you can see it here, and here are the exits of the laser beam. And we can exactly align in every hospital this block, so that we take more or less exactly the same image. Then what you can see here are first examples of the actual image from this block. What is good is that we have now real lung signal. We can see vessels, we can see the tumor, and we can see these patterns all in one acquisition. Here you can see an iodine gradient where we know, again, exactly the same position, no iodine and high iodine. So this is minus 1000 and plus 1000 more or less. And this is all in one acquisition. So we can do a technical and let's say a clinical assessment. What you can see here as well is that we also included a piece of the abdomen, although the project is focused on lung, but the same questions hold good for liver tumors. So we have found a liver tumor patient with different liver lesions. So it's a very complete data set now, which you can do the whole quantitative analysis, technical and also clinically with one block. In the same time, basically, we also tried to make an inventory of all the clinical protocols and scanners so that we know approximately how much we will have to scan this object in the different hospitals, so that we get a representative idea of well, the variation in terms of scanners and protocols, and we will try to at least broadly address the variance by scanning as much as possible different scanners. At the same time, also the team of the ETH with Ender is and the team in Sierra is looking at a pipeline, so we can submit these phantom data to a website basically, and then the post-processing analysis is done by the other teams, where we look at the effect of the different scanners. So that's also where we are right now. I think we did the first 2 runs in Basel, and then the CT physicists will now step by step visit also the other sites. I think all 5 sites of SPHN are involved in the project, and then we will get the first idea of how, let's say, the status quo of the imaging protocols for lung affect the quantitative pipeline that can be used for radiomics analysis. And what we hope to at least achieve in this project is bring out, let's say, a table where we say, hey, if you want to extract this and that parameter, you need this and that quality, and we can send the phantom and we can set up a certain quality, and then everybody knows, okay, we can only extract these parameters stably. And then you have 2 choices. Either you stick with it and you say, okay, then we can only get this and that parameter, because with radiomics you can extract hundreds of more or less independent parameters, and some are obviously more noise dependent than others. So one is, you can say, okay, then certain parameters cannot be extracted and used from our hospital, or what you could do is change your scanner settings and improve your quality. That's the choice you have. And what we could think of in the future is even add a quality label to the DICOM header that is usually used to transport these CT images, so that people can automatically say, this dataset has this quality, and I can use it for this, that, and that in a stable fashion. So that's basically practically where we are and what we're trying to do. what I think is really important, and how it's also kind of set up here, that this whole concept of thinking about calibration, thinking about automation, and then do quantification is in our hospital part of a portfolio project called the Digital Diagnostic Department. And I think also for SPHM purposes, it's really, really important, and really, I'm almost like forget about everything, but remember this: if you're doing next generation sequencing, if you do a histopathology analysis, you have to understand your data quality. Otherwise, you cannot do reasonable quantification, and that's really something I would like to get across today. The other thing is that don't overestimate the amount of, let's say, quantitative data that comes out of a hospital. It's really still something to really work hard on. And yeah, I appreciate a lot that normally it's really difficult to get funding for this because people, well, it's not very sexy, right? But I think it's really a cornerstone, and I would like to also thank SPHN for at least acknowledging that a little bit, and I really hope that we can bring this out throughout the whole hospital system. Thanks a lot.
Thank you very much, Bram. Michael, could you turn on my camera, please? So I see there are no questions in the Q&A box, but I would have a first one. So you say, Bram, when you have the chance basically to say, well, either we do not participate or we change the scanner setting, right?
Yes. So, yeah.
So is that a changement affecting in any way? Well, could an argument to not do it be that they say, well, we cannot compare then one patient with the follow-up control of the same patient? Is that a big change or is it a small change?
It would really depend on, well, first of all, what comes out of this study. It's like I don't know what to expect. Maybe we find out that only very few parameters are stable, and and that only very few scanners can actually obtain data in a sufficient quality to stably be extracted. That would be probably very disappointing for everybody in the radiomics field, but that could be an outcome, right? The problem with quality, roughly speaking, is that you have to increase the dose. So in CT, so, this is a simple statement. It's not totally true, but let's say simply speaking, it's true. So that could be an argument that you say like, okay, we actually dose optimized our protocols, and that's why the quality is so low. It's good enough for doing clinical diagnostics, but it's not then potentially good enough to do quantitative analysis. I guess that's then something you would have to discuss. But that's something I cannot tell you right now because I just don't. We haven't finished with the project yet, but I hope that's what we're gonna find out. It's like, what is the range? And there is a reasonable range of amount of dose that you can apply, and that's also what we're acquiring. It's like how much dose is applied, what is the quality, and there is a wide zone of accepted dose. So I would argue that there is room for change in these protocols. I would say that changing some things, sometimes you only have to change a little bit to get much better quality. That would not affect clinical comparability. It would only improve the images. So I would then think that if people say that, that would not be really an argument. It would maybe rather be a reason not to do it.
Mm-hmm. We have one question in the Q&A function from Marta. Marta asks, how do you define stable features in this project?
Yeah, okay, that's like basically, if a stable feature, if I extract it slightly different, it should still give the same result. It should still be, or if I look at two tumors in one data set that I both know to be aggressive, this feature should in both tumors show that it's aggressive. So, and if I measure it with a machine that has good, let's say, technical quality in one side and good technical quality in the other side, this feature, the complex feature, should also still predict something. If it doesn't, it seems to be very, very sensitive to maybe a specific machine, and that makes it unstable in a sense. Yeah, and I hope that answered this a little bit.
Okay, is there any other question from the audience? So I'm out. There is another one. So as you mentioned, the analysis of these images is computationally expensive. Moving forward, how do you foresee the landscape at different university hospitals with respect to using large computers to analyze these data?
Yeah, thanks. That's really a good question. I also one that is very important, I think, to SPHN. I think what we try to do together, well, with our SPHN node and university computational center for high performance computing, is to do as much of this at their side, because we would like to prevent to build up inside the hospital another high performance computing node. I don't think that that's efficient. I think another important thing is also for SPHN is to have a metadata catalog where you can find images without moving them, and only move them once you know what kind of project you want to do. I think there is, and that's part of actually our participation in the Imagine project, is to install a crawler that enables hospitals to quickly find collectives. And this is how we do it in our hospital as well. So we don't touch any image, we don't move it, we search it in a metadata base that is very rich, make collectives, and only after then we move the images to a high performing computing environment, preferably the high performance computing cluster in the university in our case. The nice thing there is also that if we quantitate there and derive parameters, we are only one little step away from sharing it across SPHN network again. So we don't have to move then these parameters that we extract from the hospital again to a Biomed IT node, because it's already either there or very close to where it then should be. So that's, I think, a good way to also think about it. For me, an open question is if and how we should maybe make an image, a raw image repository at, let's say, Biomed IT, so that we would move all the images there as well, so that we don't have to remove them for computational reasons. I think that's not clear yet, but I think that since there are now a few projects that have imaging data, and like I said, I'm already thinking about other data as well, like NGS data, digital pathology. Like, what are we going to do? Are we? I think there's something to say for moving this data to a computational environment and outside of the hospital, because usually a hospital does not have the infrastructure to do all the calculations, and it would make it more accessible. So I would tend to like to try it at least, and see how it works also in these projects. And then you move it once for research purposes to an environment with good computational hardware, and don't shuffle data around too much, because it creates a lot of traffic. That's really also critical in hospital structure. The masses of traffic that you then touch, it's not something you want to do 2 times for one project if you can avoid it. And then there's probably over time, if we do more and more projects in SPHN, there will be similar data that somebody else wants to analyze as well, if I have to remove it just for this project, re-find it just for this project, it would be really a burden.
Yeah, I understand. So concerning your metadata catalog, is this metadata harmonized across university hospitals? Sabine asked that. I also had it in mind because we are now talking a lot about harmonizing of metadata information. So do you know what the other hospitals have?
Well, basically, in this special case, the data comes from the DICOM header. So in the Imagine project, we try to not only look at the protocols, but also harmonize the protocols. So then there's little difference between this. The way it is right now, there's no meta database. So that would be something I think we should also discuss. It's not very difficult, I think, because we already have a structured meta database, and we would just have to think about, like, do we want to put all this metadata in one repository that is then queryable? I would like that idea, and I think, although it's, let's say, not strictly speaking scope of the project, we could at least, make first steps to do it. And because you could basically copy the instance of the crawler at the DCC, and then just consolidate all the metadata in one DCC based repository, and then you use the same search function, you use the same format, so that's basically just creating one overarching instance. I think it would be interesting. There are a lot of questions, I think, that got pushed now that we move into this field, and are really important, but that one would be one where I would feel quite comfortable that it could be solved with little effort, I hope.
I understand that the searching could be solved, let's say, with not a lot of effort. But what about then the real data requests, the images requests? So how would that work?
It works with the same software, actually. You can do the query, and then you get an answer back, and then you click on those that you want, and you can then click retrieve on a hospital base. Now, of course, if you would want to do this on an SPHN base, SPHN would have to have an own image repository. Otherwise, I wouldn't know exactly how to solve it. Probably it's possible to send the request to the hospital again, and then, but that would be more complex. And I don't know if people would want to do that, because it would create a lot of traffic as soon as you hit that button. Mm-hmm. So that's probably, you would probably not want to have an external researcher kind of triggering traffic without having control over it. So that would be one argument to say, let's create a research repository, so that, and you move it. This is how we more or less do it as well. Like, we don't copy all the raw data, but for each project we have to move raw data, and now we can keep it in one place. That was not always the case in our hospital as well. So we just on a project basis move data, but we keep it where we need it.
Mm-hmm. So 2 additional questions. If the data is centrally stored, who would control the access? Would we need a national data access committee? I mean, this goes into the direction that, at the moment we have the data that comes out of hospitals for our driver projects. We can use them in the framework of under the data transfer and use agreement, but not outside or reuse the data. So how do you imagine this could happen for imaging data in the future?
Yeah, I guess this is a sort of a time scale question, right? Right now we do it on a project base, but that cannot be the desire of running SPHN long term, I would say, because that would be so inefficient. You would destroy all data after the project is gone, and then tomorrow comes the next project that wants exactly the same, and then you do everything again. So for me, yes, I think it would be far more reasonable to have a committee that finds hard reasons not to share. And if they are not found, it will be shared. But that's my very personal opinion. That's not necessarily SPHN or Swiss truth. But I wouldn't see how how this will become sustainable. It can't be the goal to just run projects.
Yeah, and I mean, we can start with those who really agree to share, right? We don't have to include each and every data set.
I think if people, this is something we're discussing on a hospital level as well. Is like, how can we give incentives and maybe also, let's say, punishments for people who don't want to, for no good reasons.
Yes.
I think with biosamples it's a little bit different. It's because they're not endless. But here, please give me the reason why I shouldn't share. Like, and that. So I would really turn around the, let's say, the bewijslast to the person who doesn't want to share, instead of me fighting for sharing. Like, this is, I think, not smart. I think, and I think it would be relatively easy to define only a few reasons why not to share, and then there will be a national committee. It's very simple. Just find if the reasons are valid or not, and then you just say, okay, otherwise we share. And it's a paradigm shift. I know, but I think that's at least my motivation anyhow, to get away from this I sit on the data, and that's why I am important.
Okay, we have one last question. For use in research context, radiomics data typically would need to be enriched by information collected in different contexts. So, for example, from the oncology department, what are the practical challenges or bottlenecks in implementing an automated collection of data from different data sources?
Yeah, so this is basically then relating to, let's say, the other part of what the hospitals are trying to do for SPHN. It's the whole data warehousing, where we try to collect all these other features in a structural way. It is facing similar hurdles that a lot of things that happen in medicine happen in free text. But let's say if you overcome it, you just so it's, again, technically not so challenging to even add the metadata-based data to a data warehouse structure, because and then you could query everything. You could really ask, like, is there a patient with this diagnosis, with this complication, with this medication, that has an MR with this resolution and an NGS panel like this and that, and then you get the cohort back. I think that's actually what I'm aiming for, and I think that's the kind of the thing that we're now getting at, is like, how do we make raw data metadata repositories that match the repositories for clinical structured data, like laboratory, that are in the data warehouses. And in the end, I think we should be able to do a query like I just said, and then you get two things. Basically, you get an export of the things in the data warehouse, and you either get raw data or you get access to raw data on which you do your analysis. And then from this analysis come parameters that you can add to the parameters you already got, and then you do your statistics, whatever you want to do with the data.
But that would mean you would have to have a unique identifier link between them, right?
Yes, of course. Yeah, for sure. You need to know who you're talking about. Yeah, that's true.
Okay. Good. No more questions. Thank you very much, Bram, for this interesting insights into radiology and quality of radiology. I wish you all a good day and hope to see you soon in this webinar. Ein gute Miteinander.